Hi there, I'm Dr. McFerrin with DM Explains. In this video, I'm going to be talking about gain and phase margin, or the frequency response, and how we can determine stability from it. There are two important definitions that I need to give you. The first definition is the gain margin. The gain margin is the increase in system gain when phase is equal to negative 180 degrees that will result in a marginally stable system, or a system on the verge of instability. The second definition is the definition of the phase margin. The phase margin is the amount of phase shift at unity magnitude, that's 0 dB, that will result in a marginally stable system. This is a great point to pause the video and to write down these definitions so that way you have them in front of you. Now, how do we get the gain margin? What we need to do is find omega GM. Omega GM is equal to omega when the phase of the system is equal to negative 180 degrees. Then K gain margin in decibels is equal to negative the decibel gain when omega is equal to omega GM. So what I'm going to do is I'm going to find the point at which the phase crosses negative 180 degrees and make a note of that frequency in radians per second. And then I'm going to go to my magnitude plot and look at that same frequency and figure out what the value of the magnitude at that point is in decibels and take the negative of it. If you need the non-decibel value, KGM is equal to 10 to the power KGM dB divided by 20. The next question to ask is, how do we get phase margin? The first thing we look for is omega PM. Omega PM is equal to omega when the magnitude of my system is equal to 0 dB. Then I can find phi sub c. Phi sub c is the angle of my system evaluated at omega PM. And then the phase margin is 180 degrees plus phi c. So in other words, what I'm going to do is I'm going to find out the frequency in radians per second when my magnitude plot crosses 0 dB, and then I'm going to go down to my phase plot and find the value of the angle at that point. Whatever that angle is, I will add 180 degrees to it, and that will be phi PM. To recap, what that means is that is the change in phase that the system can stand before becoming unstable. For the gain margin, we have the same thing. The value in decibels that I get is the decibel gain I could increase or decrease my system by to get it to the level where it is exactly marginally stable, meaning that it's just oscillating. It's on the verge of blowing up and becoming unstable. So what I'd like to do is apply this to a by hand example and check it in MATLAB, and then we'll be done with this lecture. In this example, I have G of S, and it's equal to 1000 over S, S plus 10, S plus 1. And what I'd like to do is find both the gain and phase margin. So the first thing I should do is identify the fact that I am going to need to make a Bode plot of the system, which is the approximation of the frequency response of the system. Okay, to draw my Bode plot, the first thing I need to do is I need to break my system, which is 1000 over S, S plus 10, S plus 1, down into its component parts. So the first thing I see is that there is a gain K, and that gain K is the limit as S approaches 0. If I pull out all the S equal to 0 terms, that would be 1000 over 10 which is 100. And if I take 20 log base 10 of 100, I get 40 decibels. A pure gain will add only in magnitude and nothing in phase. So let's go ahead and draw that contribution here. This one's going to be for number 1. The second thing is that there is a pole at s equal to 0. At s equal to 0, there is a pole that is corresponding to a pure integrator. And I know what happens there is that I will be decreasing at 20 decibels per decade, crossing through a magnitude of 0 decibels at 10 to the 0. Okay, so this has a slope of negative 20 decibels per decade, and this is component 2. In phase, a pole at the origin will contribute a phase of exactly negative 90 degrees. Number 3 I have is going to be a pole at s equals negative 1, which contributes a magnitude change where it decreases by 20 decibels per decade starting at 1. Okay, so actually what's going to happen is that it's going to be 0 up until 10 to the 0, and then it's going to decrease at negative 20 dB per decade. So I've got something there. I know that's right on top of the other one. And in phase, what happens is that it will decrease by 90 degrees, but it will do so starting at the decade before and ending the decade after. So the contribution happens right there. And I would call this number 3. And lastly, the last part I should see is that I've got a pole at s equals to negative 10. At 10, that means that the magnitude is 0 until it reaches 10, and then at 10 it's going to decrease at negative 20 decibels per decade, negative 20 dB per decade, and let's call that number 4. And with the phase, it's going to start at 0 and go to negative 90, taking 2 decades to do so. So that's my contribution from 4. For the final line, what I do is I go through every frequency range and I add up everything that's happening. I'm going to do my final line in purple here. So for all frequencies, I have a gain of 40 dB in magnitude, and I have this negative 20 dB per decade from the 1 over S term. And so those add together. Instead of crossing through 0 dB at 10 to the 0, it's going to cross through 40 dB at that point. It looks like that. Then starting at 10 to the 0, or 1, I have 2 things which are acting together to each contribute negative 20 dB per decade. So now I'm going to go down at negative 40 dB per decade. So that's here. So we start with negative 20. We go to negative 40 decibels per decade. Then starting at 10 to the 1, I have another negative 20. So I add all of those up. I get 20 plus 20 plus 20. So negative 60 decibels per decade. And that will continue forever because there's no further contributions. In phase, what I'll have is until 10 to the minus 1, I have negative 90 from that 1 over S term. And then starting at 10 to the 1, I'm going to go down at 45 degrees per decade, roughly, until I hit 10 to the 0. And then I've got 2 things going down at negative 45, so I'll go down at negative 90. So that should look like this. And then after that, I go down at just negative 45. And so what I should end with is something that looks like this. It ends at negative 270 and flattens out. So that's my phase. So the final is here in purple. Hopefully you can see that. Now, what I asked you to do was to find the gain and phase margin. And if you remember, what I said was to find the gain margin, I'm going to find the frequency at which the phase crosses negative 180 degrees. We can see that that happens in the decade between 10 to the 0 and 10 to the 1. And so I'll denote that by this orange dot. And then I'm just going to draw a line straight up and see where that intersects with my magnitude plot. And you can see that it intersects pretty much right at 20 decibels. So let's write that down here. So by hand, K gain margin in decibels is equal to, if you remember from how I said I find it, I take negative, this is very important, negative the gain at that point. And I said the gain at that point is 20. So it's negative 20 decibels. If I convert this value out of decibels, that's 10 to the negative 20 over 20. That's equal to 1/10. And that's my K gain margin. What that means is that in order to make this system stable, I have to reduce the gain in the system by a factor of 10. The next thing I want to find is the phase margin. The phase margin is found by looking at what the value of the phase is at the point in frequency when the magnitude plot crosses 0 decibels. That happens right here at around 10 to the 1. And so I can draw a line straight down and look at where that's going to intercept my phase plot. That gives me what I call phi c. Phi c is equal to, if I look at this closely, it's somewhere halfway between negative 180 and negative 270. So let's say negative 225 approximately. The actual value of phi phase margin is equal to 180 minus phi c, 225. So that's negative 45 degrees. What that tells me is that I actually need to increase the phase of the system at this point by 45 degrees to make this stable. Now, what are some things that I can take away from this now that I've done it? The first thing I can take away is that a negative gain margin or a negative phase margin means the system is already unstable. And the gain and phase margin will tell me how much I need to change that gain and that phase by to make the system stable. Or conversely, if I have a positive gain margin and a positive phase margin, those mean that the system is stable, but it tells me how much I could increase the gain to make the system unstable. So that tells me sort of the bounds on my system as I start doing a control design. Now, before I end, I would like to check this in MATLAB. Let's first start by realizing that G of S, 1000 over S, S plus 10, S plus 1 is equal to 1000 over S cubed plus 11S squared plus 10S. So let's go hop over to MATLAB and take a look. So if I type into MATLAB margin of the transfer function of 1000, comma, 1, comma, 11, comma, 10, comma, 0, close those parentheses. What it's going to do is it is going to generate for me a Bode plot. Let's scooch this down so you can see it. And this Bode plot is going to be exactly the plot we drew, except that it is doing way less approximation and checking at way more frequencies than we will do by hand. And it calculates the gain and phase margin. What the gain margin tells me is that it's negative 19.2. That's the actual value. And the phase margin is negative 34.3, which is, in comparison to my originals, not that far off. If you remember, the original we calculated by hand was the gain margin was negative 20 dB, so we were pretty close. And the phase margin we calculated negative 45 dB. This says negative 34. That's because the way we approximate phase as going from 0 to negative 90 across 2 decades doesn't quite exactly capture it, but it is pretty close. We made a pretty good stab at it, a good estimate by hand. The only other thing I'd like to do is to demonstrate to you that this in fact is an unstable system. So that way you get just some additional verification. So I'm going to step that. And if I look at this figure, you see that I'm going off towards infinity. As time increases, the value increases. It goes way away from any sort of step that I have offered as the input. In the next video, I'm going to talk to you about how we're going to design controllers based on the frequency response of the system. That's all I have for now. Thank you so much for watching. Hope to see you back again soon. Bump, 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 ba-dum, bump, bump, ba-dum. And another one, bites the dust. Well, I really hope that this worked. Otherwise, I'm going to be very sad.